Well, good afternoon, everybody. For a moment, I thought I was going to be the only one here. Okay, listen, let me introduce myself. I am Dr. Fred. I will be your instructor for the next 16 weeks in Chem 130. So let me do a couple of things first. What I want to do first is I obviously take roll, make sure, gotta let some people in there. Bear with me. I'm going to take roll, and then I'm going to go over some aspects about the syllabus concerning the requirements for this class. Then after that, we'll go to the course website and run you through the website and where everything's at, talk about where you can find all the assignments. And then from there, if no questions, we'll jump right into chapter 1 and just, get it going. So if you will, or when I call your name, if you will please type in the chat. If you're not familiar with this, if not used Zoom before, down the bottom of your screen, there should be a little chat button. Click that and type in your full name. That's just record that you're here. So don't type it in yet. Wait till I call your name, please. And then type it. And then when we get through that, we'll go from there. So first, and if I mispronounce your name, my apologies. Okay, let's try Tiana Bartrio Noble. Are you here? Triana. Don't see you. Okay. How about Marbelin Camacho? Okay, type your name in, please. Just type your full name. That'll be my record that you're here. There you go. Thank you. Check you off. And then Trey Conway. If you would type your name in. Trey, there you are, Trey. Can you hear me, Trey? Yeah, type your name down in the chat, please. Okay, Angelina, I'll come back to Trey. Angelina, the amico. Okay, thank you, Angelina. I appreciate it. How about Debbie Dulac? Debbie, okay, thank you. How about Bryce Gallagher? Okay, no problem. Got you, Trey. Bryce, are you here? Bryce, I don't see you. Okay. And how about Gonzalez? Raya. Got you. All right, Ashley Hanley. I see you here. If you type your name in, please, I appreciate it. Thank you. And Kylie Ishman or Eisman. Okay. Emily Jarvie. Okay, thank you. I got Jessica Moore. Okay, Jessica, thank you. Grace Powell. Grace, thank you. And then Andrew Rulas. Andrew here. See you, Andrew. Okay, how about Trevor Sandvig? Trevor? Hey, let me double check. These are the ones I do not have. I got Tiana Bartro. And then I have Bryce Gallagher. Okay, then I do not have here today Andrew Rulas. And then Trevor Sandvig. Okay, now if I didn't call your name, probably because my list hasn't been updated. So if I didn't call your name, please type your name in the chat. I have record of it, and then I'll pencil you in, okay? Amanda. No, we don't have that one. Amanda and Ashley. Ashley we don't have. Okay, Ashley. Pettis. And Amanda. Okay. So there are two people not on the list. Okay. All right, that's the last time I'll take roll. I won't take roll when you come here. A lot of people ask me, am I required to come to class? Well, I put it to you this way. Think of it as if you were in, face to face in your class, your class, your money. I'm going to be here. I'm going to talk chemistry. So you decide. Okay. I will not take roll and count you off for attendance. However, we'll talk about attendance in general. There is an attendance requirement, and we'll talk about that in a second. It's a combination of things, not only coming here, but doing some of the assignments on a weekly basis. Okay, there we go. I see Trevor. Okay, got one coming in, so bear with me. Hi, Trevor. I see you just came in. If you would please type your full name in the chat, I appreciate it. That shows record you are here. Okay. All right. So tell you what, let me start this off by giving you my background. I've often wondered what the background of my instructors, and so I'm going to give you a little background on me, very short. And then from there, we'll jump into the syllabus. And then from there, we'll go to the Canvas course. And then from there, we jump into the actual chapter and get the ball game rolling, if you will. All right, let me make sure get the right one. Here we go. So welcome again, okay, to Chem 130. All right. Now, my background, well, I'm kind of homegrown, east of here. If you're on the 60 highway, you go east for about an hour. You eventually go right through my town, a little town called Superior. I grew up there and left there like 100 years ago. Okay. And graduated from the high school there and then left, joined the military. So I am a veteran. And specifically, I'm a Vietnam veteran. My time in the service, I was a civil engineer. Did work with construction, repair, put things together and took things apart. Okay. So after that, I ended up in Kansas City, where I pursued my education using my GFM. And I received my bachelor's of art degree in chemistry in a college. At the time, it was called Avila College. It's now called Avila University. So I got my degree in chemistry, which is ironic because the very first chemistry class I ever took, I totally bombed. I flunked it. And I'm like, no, I took it at a different college other than Avila. And it's not until I switched colleges, went to Avila. The chemistry instructor, the school was run by the Sisters of Croix de Lay. Very awesome educators. They had a way about teaching whatever topic they taught, but they made it interesting for me. And my advisor turned me around and I jumped into chemistry. Just both feet. I continued with my education and got my doctorate still in Kansas City, specifically University of Missouri, the Kansas City campus. My area of education with respect to chemistry is organic chemistry. Okay. So organic chemistry basically is my studies were making new compounds and some of these were tested for medicinal purposes and some were just made just to see if we can make them. Okay. All right. So I'm a retired scientist. My area of work was in process and product improvement. So basically, looking at a process that's been established, studying it, looking for ways to improve it, make it more efficient, make it more cost effective, looking at the products and trying to, again, make those products more efficient, more effective and so forth for the work that we were doing. So after retiring, I continued, I moved back to Phoenix. And to give you an idea how long ago that was, when I left, I-60 wasn't around. Okay, nor was I-10. That was a long time ago. Anyway, coming back here, I started teaching, became an adjunct at GCC. I've been doing that now for 7 years or so, approximately. I also started doing adjunct at Scottsdale. I've been doing here for about 3-4 years. Now, prior to that, I was also an adjunct instructor for parenting college. Most of my students there were dental hygiene, physical therapy, and respiratory therapy students. There I taught chemistry again. Also, I taught mathematics and physics. So quite a diverse background. Now, my overall experience in industry in general is quite wide. I've been in the construction industry. I've done customer service. I've been in the food and retail industry. I've even done some software programming for the company I worked for prior to retiring. And then with my late wife, I did caregiving for her. So I have quite a different background. I tend to bring chemistry or present chemistry a little bit differently, I think, from my colleagues, being that I was in industry. And while you're working in industry, you really have to be able to communicate not only with the technical people. On one end, I'm having to communicate with PhDs. And then on the other end, I have to, whatever process and product I work with, be able to communicate our ideas or gather information from the non-technical people, the people that do all that work. So I've had to kind of present chemistry slightly different. I tend to use a lot of true examples, real life, I should say, examples, things that you're familiar with. Because chemistry, it really is all around us. We're just not aware of it. Maybe not being told, this is kind of the process. As we sit there listening to me, there are tons and billions of chemical reactions occurring just in our body itself. Okay, so chemistry is all around us. Okay, I have 9 children and I have 9 grandchildren. So I'm a busy guy. All right. Let me jump into the spreadsheet, not the spreadsheet, but the syllabus. Okay. If you have any questions, feel free to chat, send it to me here on the chat, and I will answer it ASAP. Okay. So all of you should have a copy of the syllabus. I did send it out via the regular email, but it's also on the campus course. So for you to either view it digitally or print it out if you want. You can just print it out and be aware that you have access to it. Okay. So I'm going to go over some of the aspects, not all, because the rest you can read for yourself. Obviously, this is a Zoom class. You all are here, so you know how to get to it. We're going to be here from 1:30 to 4 o'clock. We'll probably take like a 15-minute break about halfway through and then proceed with, after that. So about, I don't know, about 2:45-ish, we'll take a 15-minute break and then come back and finish up the rest of the hour and 15 minutes or so. Okay. My name. Now, to communicate with me, the official way of communicating with the instructor is to Canvas email. Now, Canvas email has a great advantage rather than using my EDU email address. And why is that? Because all the email I get from Canvas, it's tied into my cell phone so I can access it quickly. Plus, it's only email from you, okay, my students. I do teach at GCC, so I have 3 sections, but all that email is sent straight just from my students. My EDU email address, I get a ton of emails of everything from the whole Maricopa community family, and your email can get lost. So If the Canvas email is not working, then by all means, we'll use the EDU email to get a hold of me. And obviously, I'll keep an eye out for email. But nevertheless, primarily use the Canvas email to contact me if you need, if you have a question. Okay. Which, by the way, during the Zoom, we have an occasion, Cox decides to say, okay, I'm done, I'm tired, and take a break. If we get cut off, okay, just log out of the system. I'm going to do the same. Wait a couple minutes, I'll get it running up again and come back. Okay. If after the second try we can't get through, then I'll shoot out an email and say, hey, we got problems. We'll have to call it a day. Okay, but give it at least one attempt of getting back online if we get disconnected. And this happened in the past. Course description, there's a breakdown of all the course competencies, which is all the material as per MCC, the Maricopa Community Colleges, deal with chemistry and what we're going to cover. Okay, quite a bit of information. Text, well, you don't have to buy a text. The text, if you've not seen this already, the textbook is in PDF format. Okay, so you don't have to buy anything. You have access to it. You can print it out if you like. It's totally up to you. But some students still want a textbook. You're welcome to get a ordinary, general chemistry textbook, or you can go there. Option number 2, they do offer a free download of a textbook. But sometimes these textbooks give you a lot of other information and that you may not need. So, but it's up to you. You have access to it. You will need a scientific calculator. Now, you don't need to get one of these high dollar, $300 calculators at all. I think most of them are running somewhere $15, $20. What you need is a calculator that can do what is called scientific notation. Okay, so check that calculator, see if it can do scientific notation. And what that is, just a shorthand method of inputting and writing, if you have to write it out, very large numbers or very small numbers. Okay, so make sure your calculator can do that function. Give you an idea, we're going to be dealing with numbers like 6.02. Move that decimal point over 23 times over to the right. That's how big this number is. Some of these numbers will be working with. So, and that's kind of difficult to input that number in the calculator. Most calculators won't accept it if you try to do it longhand. You have to input it in scientific notation. So make sure your calculator can support scientific notation. The only tool we're going to be using is Zoom. Obviously, we're here, so I'm going to write that in. All the Zoom meetings, like right now, we're being recorded. Okay, I do have a YouTube channel which I upload all the classes that I lecture here, and so you can view them later on, or view them again, at your leisure. Or sometimes you miss a lecture and you can't make it for whatever reason. You have access to what we talked about. Along those lines, as far as recordings, not only are we recording our Zoom lecture, you have, and you'll see this in the modules of the course, you'll have free videos concerning the chapters. Dr. Ken Smith from DCC has created a Zoom videos concerning every chapter that we cover. And I put them in the module so you can, if you want, get a preview of what we're going to talk about by an alternative person talking about that topic. Sometimes if there's a concept that maybe you're having a challenge with, maybe I'm not presenting it in a manner that you can, click. It does help to maybe have another person present and say, whatever it takes for you to understand what are all the concepts we're talking about, whether I present it or another person. You can go to YouTube too and do a search, and you'll find tons of videos concerning the topics that we cover. So you have a lot of resources. The other tool we're going to use is called the Responsive Lockdown Browser. Okay. Now, point number 1 about this browser is the browser that we utilize is specifically made for all the Maricopa schools. Okay, they have designed it for the Maricopa schools. So if you go online and you go to your someplace and you download a quote generic lockdown browser, it won't work for us. Okay. It has to be specifically one made for us. And I have included in here the link for you to download via a PC or a Mac computer. Okay. We also have a little activity for you to check to make sure the lockdown browser is working. What that does is it's a browser that keeps you and logs when we take exams. The only time you need it is when you take an exam. And it prevents you from going to other sites. And it keeps a log in case you do move to other sites, and that triggers you searching for answers someplace else. Okay, so don't want to do that. So do use the lockdown browser, test it out, make sure it's working for you. Both the PC and the Mac computers support it, and I'll also set it up so iPad, if you are using the iPad, there's the link to go to your Apple Store to get the lockdown browser. Okay, there's a study guide concerning the lockdown browser. Welcome to download it and read it, but basically once you download it, what it does, it makes you shut down all other programs before you can log into the Canvas course. And then what it does, if you're not used it before, if you used it for any Maricopa school before in another class, you don't have to download anything. It's the same one. Okay. But if you haven't, what happens is it will load up to your system. And then whenever you need to take an exam, you go log in through the lockdown browser. Okay. And you log in like you normally do. And that allows you to go to the assignment and complete it. If you try to go through the assignment through the regular browser, it's going to notify you, no, you can't do it this way. You got to go through the lockdown browser. Okay, and some technical requirements concerning your system, concerning the lockdown browser. Now, I am not using the web part of it. I'm not looking at you. I won't be looking at you in your web camera, anything like that. Okay. It's just the lockdown browser part. Okay, well, grading and standards. Okay, while we have a couple of sections here, we're going to have homework, okay, online. There's 15 homeworks, which I believe the lowest three are dropped. The lowest three scores are dropped. And those homeworks consist of about 15% of your grade. I'm in the process I'm up to chapter 6 right now. I'm adding to each module practice quizzes to give you another resource to help you out with practicing taking exams and quizzes. Okay. So I'm up to chapter 6. I'll see if I can get the rest of them done as soon as possible. Now, with respect to homework, every homework has 2 attempts. Now, what students have done in the past that works out pretty good is they take the first one kind of cold turkey, if you will, just to see where they stand. Then wait until we cover that chapter and then take the second attempt. Okay. That's one way of doing it. Or you can wait until we cover the material and then, take it, or any way you want, whatever you're comfortable with. Okay. It will keep the best score of those 2 attempts. And we'll talk about due dates. Everything there's no time limit on the homework. Theoretically, you can take all semester, but that's not realistic. There's no time limit, but there is a due date. Now, a thing about due dates, I will not give you a due date. I will give you a due date of a particular homework assignment after we're done talking about it. If we've not finished talking about it and the due date is the next day, then obviously it's not due. I will move the due date. Okay. So if sometimes I forget, don't freak out. You might think, well, chapter 2 is due tomorrow. Well, we haven't done chapter 2. Don't freak out. I'll eventually catch up and move it. I don't expect you to do the homework unless we get done with it in the lecture plan. Okay. Having said that, it will have a due date. Okay. So if you don't do it by the due date, there is a penalty involved, which consists of 5% per day until you reach the 50% mark. So 5% per day, that's what, 10 days, okay, of taking 5% off. So eventually day number 11, what happens after day number 11? The maximum number of points that you can get for that assignment is 50% of what it's worth. So if an assignment is worth 10 points and you go in there and it's late, day 11, you're running late, the maximum number of points you can get would be half of it, okay? If you all got everything all correct, okay? Point being is all of the assignments, except the homeworks that have specific times, the homeworks are due, can be done, will be open, let me restate this, are open until the last day of class, but with a penalty. So if you miss one, you can still go back and do it, but some points is better than 0 points, okay? So you do have access to it until the last, I believe it's the 16th of December, that all the homework gets cut off and all the late work converts to 0, or the ones you missed converted to 0. All right, so that's 50% of your grade. All right, there is a special exam as designated by the chemistry department of SCC. It is called the nomenclature exam. Okay, it's worth 10% of your grade. Now, what this is a nomenclature is a fancy word for name that compound. So basically, you'll be given structures, and then you'll be asked to give the name, or you'll be given the name, asked to give the structure. Okay, and for the online exam, the nomenclature exam, you have an unlimited attempts. So you can take that as many times as you want up until December 16th, okay? But as per SCC Chemistry Department protocol, you have to score at least an 80% to get the 80% credit or better. If you don't score the 80%, it gets converted back to 0. Now you might say, well, okay, it's only 10% of your grade. Okay, that's correct. However, if you're on the border, let's say you're on the lower end of an A, that 10% can drop you into the B. Okay. Or if you're in the upper end of the B, that 10% can prevent you from getting up into the A range. Okay. So depending where you're at, that 10% can affect your grade. To go from a D down to an F, or from an F back up to the D, wherever you're at in the scale. Okay. Now, what I do about halfway through the semester, because Canvas does not grade, incorporating your grade, anything that hasn't been graded. What has happened in the past is the people that don't take that nomenclature exam get no grade, right? So they're thinking they're doing well, and then toward the last 2 or 3 weeks of class, I have to put in a 0 because no one's attempted it. And then the grade all of a sudden, boom, drops drastically and people freak out. Now you only got 1 or 2 weeks at the end of the semester to kind of catch up and get that 10%. So to prevent that, about halfway through, what I do, if you're not taking that, I throw in a 0 to give you a true idea. And I'll remind you when I do that, I'm going to put a 0 in there if you're not taking it. So you get a better feel for what your grade truly is, okay? All right, because I don't want you to wait the last 1 or 2 weeks and get all stressed out because you're trying to pass that. I've had people who take one time and do twice and they're happy with it, got the 80%, you're done. I've had people take it, 20, 30 times and have a challenge for whatever reason. So, and they get stressed out. So I don't want to stress you out with that. So I will put a 0 in there about halfway through the semester. Okay. Lecture exams, we will have 5 lecture exams, okay, and which are worth 35% of your grade, and then your final exam, which is a comprehensive exam covering all the chapters, which would be worth a total of 15% of your overall grade. Okay. Now, if you miss an exam 1 through 5, things happen. Okay. If you know ahead of time that you, for whatever reason, you have to miss that day, I have no problem to move the day, that test exam, move it a couple of days forward, maybe a couple of days, after to help you out. Okay, but if you can't make it in that time period and you have to miss it, no problem. What I do is I would take, for one exam, one missed exam, I would take your final score percentage, the final exam, and substitute for that missed exam 1 through 5. I can only do that for one, okay? For one exam, keep that in mind. Let's see. Lab experiments. So you're going to be quite busy. Some cases interesting that SCC, the labs and the lecture are all one group, one unit. At GCC, it's totally separate. So the students take the labs separately than the lecture. You up there, you may have the same instructor, you may not. Okay. Here, we would be, if we were in person, you'd be every Friday, we'd be in the afternoon, we'll be doing the labs. What we have here is 11 labs, okay, online. It consists of, basically looking at videos and then answering questions based on the videos and the observations of what you see in the videos. There will be 2 lab exams. The first one's a midterm, and then a final live exam. So the first one takes, it's an exam for the first half of the exams, like I think labs 1 through 6, or it could be labs 1 through 5. And then the final exam is the remaining labs 6 through 11. Okay. They are worth 25%. You only have one attempt, but no time limit. And they can take, as in person, they can take 2 to 3 hours of doing this. So, give yourself plenty of time and to accomplish those exams. Again, you may not do it. And so obviously, after the due date, there is, like the homeworks, a penalty, which is 5% per day. And these labs are worth 100 points. So after day number 10, which is 11, the maximum number of points you can get would be 50 points. Okay. If it's after the due date. Okay, a grading scale, slightly different than a normal 90-80. It's 88, 78, 65, 50. Okay, so it gives you about 2 more points, wider range for each grade. Okay, there's your grading scale. This is a breakdown of the assignments. There's 15 lecture Canvas homeworks. The lowest 3 will be dropped. That's 15% total. 5 lecture online exams, 35%. 1 nomenclature exam worth 10%. And then 1 comprehensive final exam worth 15%. And then the 11 lab experiments with the 2 exams total are worth 25%. In the grand total, 100% of the grade. Okay. Any questions so far? Okay. Right. Response time, meaning you have a question. I would definitely, if I can, respond the same day. If not, give me at least 24 hours. You got to sleep a little bit once in a while. Okay. Primarily use the email through Canvas. And if Canvas is not functioning, and that has happened in the past, go ahead and use the EDU email and address. Okay. Which brings us to attendance. Okay. Attendance consists of, for online classes, consists of attending the Zoom, that's part of attendance, and doing your assignments online. Okay. If you have 5 or more missing assignments, and I can see that you're not logged into Canvas in at least 2 weeks, then that is enough criteria for me to drop you from class. Okay. I keep track of it. I check when you log in and what you've turned in. If you ever reach that point, I would send you an email to remind you where you're at. Okay. So attendance consists of both doing the assignments, so which means you got, think about this, you got the lecture. We're here for what, 2.5 hours. We're here for that. You got a lab once a week. You have homeworks do, okay? So that's a lot of online work that you need to, all that is attendance. Okay. I'm not requiring you to be here for every Zoom. If you're here for every Zoom, of course, it's to your advantage. All right. Any questions at this point concerning that? Right. This, we have online, here's some information concerning online tutoring. There's also on-campus tutoring that you can access. Okay. Withdrawal policy, there's a deadline that you may want to read about when, if you need to withdraw, that you can do it on your own. After that, then it's left on instructors' permission to get a withdrawal. Now, if you take the final exam, I cannot, and you request a withdrawal, I cannot do that. Okay. That, some people wait, well, let me see how I do in my final and see if I pass. Well, I can't do that. So think carefully if you are requesting a withdrawal. Keep that in mind, that if you take the final, I cannot give you a withdrawal. All right. All right, so much for all that. There's all this stuff here you can read on your own. This is a breakdown, and notice keyword up in the very first line. SCC 10130 tentative class schedule. Okay, and it's tentative because the times, I try to keep them. For example, the first exam we got scheduled for the 9th, September 9th, and it's the 10th. Okay. And the 9th is that Friday. My exams will be available to you, and I'll explain here in a second, on Saturday. Okay, for you to finish them up, to do them. But, and I say tentative because it depends on how we proceed with our lecture. I have no problem with moving the exam over 1 week if necessary, but it all depends how we come along with chapters. Obviously, I need to, the next 2 weeks, I need to complete 3 chapters and talk about that. Okay. Excuse me. If you look at the far right, those are the labs due on that week, Friday of that week. Okay. All right. So what I've done is I make the labs, the exams available from like a minute after midnight on Saturday, and they shut down right before midnight. So you have a lot of hours, 12 hours available to you to complete that exam. And they do that because there are some people that work night shift and get off early in the mornings and prefer to take that exam there. And it depends on their work schedule. So you got 12 hours to take that exam. The exams themselves are timed 75 minutes. So keep track of it, knowing that they open up at midnight, they shut down at midnight. Okay. That you give yourself at least, 75 minutes, 80 minutes of time to complete that. Okay. Don't wait until like 2 minutes till the time shuts down, because Canvas will pick you up. All right, let's see. If you complete the nomenclature, some people have, if you can complete it before September the 16th, in other words, complete it with respect to getting that 80% cutoff, there is a 1% little bonus. Okay. It's 20 questions. It goes, if you get them all right, then you get 22 out of 20. And you can tell a bonus. If you do it and I forget to give you that 1%, let me know. I definitely will get that corrected. Your first online exams there are the week October the 7th. You notice it covers exams 1 through 5. And then we have no lecture or lab on November the 11th. That is Veterans Day. Okay. So we may need to adjust the lecture a little bit, given that we're not here on Friday. And then Thanksgiving break is the 24th through 27th. And then we have December the 9th, which will have the final exam number 2 for labs 6 through 11. Also, we have exam number 5. Now, what we probably have toward the end of the semester, we will probably have maybe a couple of lecture times on Fridays that we have completed all the chapters, lecturing and talking about them. And so those days I will be here, and those are like study days. They're open for review, for anything, any questions that you have, we can go over things. So and generally I get about 1 or 2 of those sessions toward the end of the semester. Okay. And so the last exam number 5 is December the 10th. And then the lecture, and this is important, is on December the 16th, not a Saturday, because officially the school ends on the 16th. Okay. So, and that is the last day that literally anything could be turned in if you not turn anything in. All right. Let me see. Any questions concerning the requirements? It's all there. Any questions? Feel free to shoot me an email and I can go over it. All right. But what I want to do is, and this will bring us right to your kind of like a break time, if you will. So let me go over the course itself on Canvas and go over some aspects about it. Okay. Your homepage is as follows. So you can see here that there are modules. The course is set up with modules. Now, SCC put in the welcome module. So there's things in there that belong to me, things in there that belong to SCC. The important aspect here is the third entry called tables to print. Those tables you're going to need, you're really going to need a hard copy of them, because you can't really access them during the exam digitally, because your lockdown browser won't allow you, for one. And if you found a way around it, it would come across and log you as you were someplace else other than in the exam. And so what that is print those two, because we're gonna this is the periodic table. It's a little bit marked up with information. We're going to use this quite often. It is our go-to table that we use quite a bit. Okay. In this table, you see in the bottom left corner, there's another table with what is labeled as polyatomic ions. We're going to use that quite a bit. We have what's called an activity series that's going to help you out with respect to certain types of chemical reactions that allow you to predict whether this reaction will proceed or not. Okay. And then we have a solubility rules that with respect to aqueous systems, water-based solutions, that we can predict the compound, whether it be soluble or insoluble in water. Also helps us predict certain types of reactions. Okay. The other table is called the shapes table, which is this one. Okay. There is some equations there for you. You don't have to look it up. You have access to them, specifically converting units of Fahrenheit to Celsius and vice versa. There's conversion factors here that we give you, that 1 inch is equal to 2.5 centimeters. 1 pound is equal to 454 grams, 1 quart equal to 946 milliliters. We're going to have a chapter where we're going to be using a technique to convert factors. And this particular technique is very important because we're going to utilize it when we start working with chemical reactions. Okay. It's a matter of keeping track of our units, and our units can really tell us if we set that problem up correctly. The other important thing is here, there's a table called Table of Molecular Shapes and Botany. We will reach a point where we will start with the elements. I got them back here. From the elements, make compounds, and the compounds will then, from the compounds that we make, we would create or generate what we call a general formula, generic formula. Okay. And that information, depending on the compound, what it is, will give us what the molecular geometry. So a general formula of AB4, for example, has a molecular geometry down here in the middle, in the second column, and it has a specific name, tetrahedral, and a specific bond angle. So that table is very, very important, okay, for us to predict what type of structure a compound has. Okay, let me go back through the course. Well, on your far right, you have a to-do list that helps you out to determine, hey, what's coming up, what I got to do. All right, now, SCC put in a module called First Steps, helping you to succeed, and so forth. I put in another module that will help you with learning how to take notes and, pass chemistry as the way it was labeled. But the important aspect of this is a lot of information here, please read it at your leisure. These techniques can be utilized for all your courses. There's certain techniques of note taking can be very helpful. There's no right way or wrong way. Okay, that's the thing about taking notes. What the right way is what works for you. And sometimes you really need to be shown certain methods, and then from that information, draw what works best for you. Okay, so you can utilize this information not only here, but throughout your academic career in taking notes. But it's very important. One word of advice about taking notes was given to me in my research advisor when I was in graduate school, 40 years ago or so. He said that whenever you write something, a note, write it in a manner so that 5 years from now, when you read it, you know what you wrote. You know what it's just like, okay, I understand. Sometimes we write notes and we're like, what am I saying? What did I write here? What does that mean? You forget. But if you write it with a sense of, am I going to be understand what I wrote 5 years from now? That can help. I've used that throughout my career. It has helped, especially when I got into a professional legal situation with patents and so forth. I had these notes there to fall back on. It really helped out. So also write it so that other people understand something. We have a lot of short answer questions. Okay. Think about how you're writing. I know what you're thinking up here, and sometimes what you're thinking up here doesn't come down to your hand. And so after it comes onto your hand, step back and read what you wrote. Does it make sense? Okay. Because remember, I got to read what you wrote. And I know you're talking about, say, compound A, but if you're talking about it, I don't know what it is. Okay, so keep that in mind. I've added some additional resources. These are simulations that we'll go over them once we get to that point, to help you to understand how an atom is put together. Helps you to understand balancing equations. We're going to have to balance equations. Talking about molarity, a very important concept in chemistry, molarity. And one about the probabilities. This is more FYI. You click it, it gives you information about a particular element and what it can be used for. So additional information. Okay. In the nomenclature module, not only do you have the test, the nomenclature test itself, but there's some files in there that help you with respect to different types of how to name compounds. Okay, so it's additional information. I will eventually, when we get to this point, I got a PowerPoint slide here in the document, and then I'll go over that to kind of help you out with some of these are called oxy ions. Okay. I know right now it's all foreign. I'm just telling you now. Here's some information for you, which then brings us to the particular chapters. You have 15 modules, 16, excuse me, I forgot the gas modules for every chapter. Okay. In every chapter, if you click on that, you will have an overview. Okay. There's an overview for that chapter, what you're going to talk about, what the whole chapter is about. You have the textbook for that chapter right there in PDF format. And you have the videos, not the videos we're making here as we do the Zoom. These are the pre-made videos that Dr. Kim made concerning chapter 1. So some people like to go in there and listen, not only read the chapter, but listen to the chapter so you can be aware of the subject. And then we come in and talk about it. So you get a double whammy, if you will, right? And then there is a worksheet for that chapter covering problems for that particular chapter. Okay. You got the homework. Okay. And I've included in there in PDF format the PowerPoint slides. Okay. For the ones I use for that chapter, because some people like to print out the PowerPoint slides and use that to write notes on. So it's available there for you. And then we have an activity here. I thought I have okay, I don't know. I haven't dumped them over yet. I have practice quizzes that I need to dump them over. And I'll get those to you as soon as you can. Okay, there is an extra credit. It is a practice lockdown. It's a test for the lockdown browser. So go download the lockdown browser, go through what you got to do to get it on your system, and then open up this assignment. And it's a short couple quick answers to tell me yes, it works, or if there's a problem, let me know what's going on, and you pilot your points there to do that. Okay. And so the same, all the chapters are, oh yeah, it is. Chapter 1 did not have a practice. So starting at chapter 2, there it is. We got a chapter 2 overview, also the text file, videos, pre-made videos for chapter 2, the worksheet, a practice quiz for chapter 2, the homework for chapter 2, and then the PowerPoint slides for chapter 2. Now, what about the PowerPoint slides? I have adjusted them as needed. You have all the ones I use, but there's some power slides that I don't use. So you'll see when I go through it, you just make a mark to it. I'm not using them, but they're still there. Okay. All right. So now, if you go all the way down to the end, you have the final exam section, the module. Okay, it's the same practice lockdown, but I put it there too again, so it's to refresh your memory here. Because this is important. It is important that you check your lockdown browser way before you take your first exam. And you don't want to wait until the first exam day, and then you're messing with the lockdown browser and you're having a challenge. Because you want to take care of that right away, early in the semester. All right, so you have the final exam, obviously won't be open until December 5th. You will have an evaluation for me. It won't be open till the 16th. And then I've included in there a practice final exam for you. Both the exam with the key and without. Okay. And then finally, the labs themselves, the online labs, we have here lab number 1, and then all the way down to the last lab, lab number 11. And then you have in there the midterm exam for the labs covering labs 1 through 5, and then the final exam for the labs covering labs 6 through 11. Okay. And again, I've included the PowerPoint slides for the PowerPoints that I'll be using in my lectures. Okay. Now, what I've also added for you is if you go over here, obviously you know where the Zoom is because you know you're here, but to go find all the lectures that we record, I got the link for it, so it will send you to my YouTube channel, and you will find not only your class, but I label my SGCC. I got a 1 o'clock and a 4:15 class, so you're going to find videos there with their chapters. And what I try to do is maintain, like right now, my GCC class almost finishing chapter 1. You guys, because I spend more time with you one day, would probably be in the same spot, maybe into chapter 2 when we get done with all this here. Okay. So you're welcome to view those videos too. Also, FYI, I do my GCC class at 1:00 is one section and 4:15 is another section, Tuesdays and Thursdays. You are more than welcome to come to those days if you have the time. If for some reason you know ahead of time you can't come to Friday, by all means, feel free to come in Tuesday and Thursday and catch up on or go over what we're going to talk about, because like I said, I try to maintain all 3 classes to be within a few slides of each other with respect to the chapters. Okay. So you're more than welcome. I've also invited them to come to the Fridays if they need more chemistry, if you will. So I do communicate with email, but I also use announcements. So down the next click on the left is announcements. I've already added some material in there that you may want to go in there and read about, having to do with a lot of topics we're talking about. But SCC also adds other things in there for you. So there's a variety of different things in here. Right now, I don't think SCC's added anything yet, but most all of this is mine. So feel free to go in there and get more knowledge about your course. Okay. The syllabus click is I got my little cartoon there. About 99.9%, nothing's ever 100%. 99% of everything you need to know is in the syllabus. Okay, if you don't see it, let me know. I'll make sure you get that information. I like the syllabus button because it does break it down here of what's coming up and what's due. Okay. The next click is the modules. We run through that, or if you want to just look at the assignments itself, you can click on the assignments. Okay, and these are broken up into the individual assignments. All right, now I've added what's called a study mate here. Okay, if you click on that, let me do this. I need to leave the. Oh, there it is. It's there. Okay. I wasn't seeing it in the other view. Okay. Up on the top here, under Study Mate, there's a link called Nomenclature Practice. This is related to the nomenclature. Just because we got a chapter nomenclature, you're going to have nomenclature naming compounds throughout the semester. I will start introducing you how to name these compounds as we proceed. Okay, so nomenclature is the language of chemistry. Okay. All right. So if I click that, I've uploaded, I think, about 140 some compounds, names and formulas to do a couple of things. One, I would only use the flashcard and the matching part of this. I tried looking at the other choices, and some of the names require parentheses, and this study mate doesn't recognize parentheses. So, for example, if you click on the flashcard, okay, it would give you a name of the compound, manganese, Roman numeral 2 iodide. What you now have to do is figure out the formula. So you write out the formula on a piece of paper, and then if you want to double check, you flip the card, and there is the formula, Mn and then I2. Now keep in mind that this doesn't support subscript. Normally that 2 will be a subscript to show you there's 2 iodides. Okay. Now the other thing is you can go to the next one here. We got another name, manganese 2 nitrate. Okay, and then there's the formula. Okay. So flashcards are pretty good. There's 143 flashcards, 143 different compounds. Okay. The other one that works pretty good is called matching. It takes that same 143 and it creates here. In this case, it gives you the name, and then you need to figure out what's the formula. Okay. and it's called 10, Roman numeral 4, carbonate. I know right now it's all Greek to you, but we would definitely, you're going to reach a point where you would understand what that means. And when you do that, you would then click on that and you would know, oh, I got it right. That is the formula for 10, Roman numeral 4 carbonate. Okay. And when it comes to nomenclature, we need to be able to go both directions. In that one, we're given the name to determine the formula, and vice versa. If we're given the formula, figure out the name. So you could be given this formula and asked to name it. Okay. So there's an additional resource for you to help you out with the nomenclature. All right. I believe double check to make sure. Go back to student view. And we have the grades obviously here for you. Okay, and then a link for the library for you. Okay. All right. Any questions? Well, I have 2:30. Tell you what we do. Let's take a quick break. Maybe you'll have a questions during the break. And if we'll come back in 15 minutes. If you have any questions concerning what we just talked about, I'll go ahead and answer. If not, I'm going to jump right into chapter 1. Okay. All right. So I got 2:32. How about 2:45, 2:47? Okay. We'll be right back. Can we pause the recording? Okay. Any questions before we continue? Everybody know where you need to get everything you need, files, PDF files, where your assignments are, the percentage of all the assignments, et cetera, et cetera. Okay. If I sent to everyone their office hours, which I stated I'm not required to have them because I'm an adjunct, but I do have them available in there. So they're by appointment, Tuesday and Thursday. I have a free time between 3 and 4 in between classes. So if you need time to, got some questions, send me an email and I'll make sure I open up the Zoom for that time period. Okay. Also, if you're interested, my GCC lectures are Tuesdays, Thursdays. I got the 1 to 2:15, 4:15 to 5:30. Like I stated, feel free to drop by and go, listen to what we're going to talk, which would be the same similar stuff to we're doing here. Okay. All right. Any questions, comments, concerns? No. All right. Well, let us jump right in there. Let's put your tables in the upright position because we're taking off. Now, the first couple of meetings, we give you a lot of information, and so it eventually things kind of settle out. But in the beginning, things can get a little hectic. So let's see. We can run through it, get through it smoothly. All right. First chapter deals with matter. Okay. And what are we going to talk about this semester? Well, first of all, we're going to define chemistry. Chemistry is essentially the study of the composition. All chemicals have a specific composition. In fact, when we get down to the formulas, they come together in certain whole number ratios, certain atoms, like carbon dioxide, for example, that contains 1 atom of carbon and 2 atoms of oxygen in that particular structure. We're going to learn about the structure that shaped table that I talked about earlier. We're going to use that shaped table to actually determine what the 3-dimensional model of that compound, what it is. And keep in mind, these are current theories of what things look like, okay, and what things are doing. Best theory that we have today doesn't mean that it won't change. Doesn't mean it's 100% correct. Like I said, nothing is 100%. Yeah, I don't know if anybody tells you that, they're not telling you the truth. Because the whole model of how our atoms are put together could change tomorrow with new information, but it really hasn't in the last, I don't know, 80, 90, 100 years. It's, in fact, we've built on it, and it's going along pretty good. All right, so we're going to talk about the properties, what kind of properties are involved with chemistry, with compounds. And we're going to learn why certain things have certain properties, why things, for example, liquids like water compared to honey, why water, when we compare the flowing, why water is less viscous than, say, honey. We don't know if I had a cup of water and a cup of honey, and I get them together and flip them, who's going to win the race? Obviously, the water, okay? And it has to do with the properties of the water compared to the honey molecules. We're going to talk about physical and chemical changes of matter. Now, keep in mind what's important about physical changes is this. When we go from one physical state, meaning we go from, and we're going to talk about three physical states, solid, liquid, gas. When we go from one physical state of solid and move it to a liquid and then move it to a gas, nothing happens to the structure of that compound. Okay, for example, ice. Ice is nothing more than water, good old-fashioned H2O, right? Two atoms of hydrogen and one atom of oxygen. When it's in the solid form of ice, it is still H2O. And when we heat it up and make it into liquid, guess what? It is still H2O. We've done nothing to the structure. And we continue to heat it up, we form vapor, it's still H2O. The structure remains the same. That is a physical change. Compared to a chemical change where we can take water, good old-fashioned H2O, and hit it with a current, and we can break it apart. We break it apart into its components of hydrogen and oxygen, separated. That is a chemical change. A chemical change is where we destroy the starting material and we create new material, okay? Well, what we know is this, that all matter is made up of atoms. And the atoms themselves, the model that we have is as follows. In the center is a proton. And along in the center, in the nucleus, is a neutron. So we have in the nucleus, in the center of the atom, the proton exists and the neutrons exist. And then our motto is that the electrons, which are orbiting around the nucleus, is where the electrons are. Okay. All of these together, the weight, the mass of the proton, the neutron, and the electrons make up the atomic mass of the atom. Now, the amazing part to me, and since that's what really caught my interest in chemistry, is the electron. Those electrons, when we compare the mass relative to the proton and electron, are extremely tiny. The electron mass is so tiny that by what we consider it as any mass, we give it a value of 0. The mass of electrons, for all intents and purposes, is 0. It's massless, but it's not. We know it's not. And even with that little bit of mass, it has a humongous effect on the properties of chemicals. It has a humongous effect of literally everything in chemistry. All the action, all the stuff happens with electrons, okay? Now, one note about protons. The protons define the element. There's 118 elements that we have, okay, known, okay? And each one has a specific number of protons. Element number 1 is hydrogen, has 1 proton. Element number 2 is helium, has 2 protons. We can lose neutrons, lose and gain neutrons and electrons all day long, and it doesn't change what that element is, okay? As long as if I got one proton, that's hydrogen. It could have an extra neutron, no big deal. It can have more electrons, no big deal. It's still hydrogen because the proton defines what that element is, okay? It defines, and if we lose a proton, we literally create a different element. We're going to talk about chemical bonding. Now, there's only 2 types of chemical bonds that occur. Okay, you would think there would be like all kinds of chemical bonds, but there's only two types. All right, there's a one type. The first type consists very specific type of atoms. We'll have more detail on that later. But think of them as two magnets coming together, and they attract each other. Okay, and they're being held together like two magnets. That's one type of bonding, chemical bond. In fact, we call that ionic bond. The other type of chemical bond is where these electrons again, here we go, electrons again, are actually being shared between two elements. And think of them as my fingers representing the electrons, and they're interlaced with another element. The fist, the main part of my arms represent the two atoms, and these electrons are represented by my fingers, and there's overlap, and they're sharing that bond. That's a covalent, what we call a covalent bond. But there's two types. That's it. One where they're sharing electrons, and the other where they're not. Okay. We're going to discuss the periodic table and the trends of the periodic table. We're going to use the periodic table like the one behind me, and given any element you've been asked, just by its position on the periodic table, determine whether it is a solid, liquid, or gas. Okay, just by its position up there. We can also determine just by the position when comparing two different elements, which one's bigger. You know, is hydrogen bigger than helium or vice versa? Okay, by knowing its position and by knowing some principles about what we're going to talk about, you can make that determination. Okay? These are periodic trends here. We're going to talk about acids and bases and electrolytes. Well, a classic acid, which I use quite a bit as an example, is the acid that's occurring right now in your stomach. That's hydrochloric acid. We carry that acid 24/7, okay? And if you carry too much, let's say too much Taco Bell, you got a little bit of acid reflux going on, a little heartburn. What do? You take something like Tums or Maalox. Well, guess what that is? That is a base. And when you combine an acid and a base, they neutralize each other. Hence, one of the 6 types of chemical reactions called a neutralization reaction. When you ingest the Tums, it neutralizes that acid. Electrolytes, I'm sure you're familiar if you're one for keeping track of your electrolytes, you're working out in the sun, and you've got to drink drinking water by itself. It's good, but you also need electrolytes. Okay, these electrolytes are nothing more than these elements behind me that have either gained or lost electrons. Okay, when you're drinking sodium, you're not drinking the sodium element, you're drinking the electrolyte sodium, the ion. Okay. Now we're going to talk about mole, right? No, that's the first time I saw that. So we're talking about mole. No. The mole is nothing more than a number, and it just happens to be a humongous big number. Okay, it's called the chemist dozen, because we all know, for example, when we say 1 dozen, okay, we know that is equal to 12 units of something. Okay, a dozen, when we say a dozen, you got 12 of this, 12 of that, whatever it is. A dozen. When we talk about 1 mole, well, it's our number too. It just happens to be a humongous big number. Specifically, this is where the scientific notation in your calculator comes into play. Okay, now if you would take that decimal point and move it over to your right 23 positions, you have this big number. And that's a lot of zeros to write. So what we do, we write it in scientific notation, represented by the number of pi times 10 to whatever power of decimal places you need to move. To give you an idea how big that number is, if you were to count 1 number per second, 1, 2, 3, 4, 5, 6, and you want to get to the end of this number, I'll see you in a couple of thousand years. That's how big that number is. Okay. So that's what the mole is. 1 mole is a big, humongous number. Very important concept in chemistry, because we're going to learn that to get from point A to point B, from chemical A to chemical B, when doing our calculations, if I have X grams of chemical A and I want to calculate how many X grams of chemical B I need, I cannot go directly from grams to grams. What I got to do is I got to go through this unit moles. I got to convert the grams of A into moles. And from that information, I can now convert to grams of B from the moles. Okay, so very important concept. The next one is a fancy word here called stoichiometry. Okay, you're all familiar with stoichiometry. Okay, if I said to you, okay, you got a car, obviously, how many tires do you have in that car? Well, you have 4 tires, right? And you have one frame, one tire, one car, right? The stoichiometry, the relationship, the ratio between the tires and the car is a 4:1. If this was a bicycle, that ratio would be a 2:1, right? 2 tires for one frame of a bicycle. If it was a unicycle, that ratio, that stoichiometry of the unicycle would be a 1:1, 1 tire to 1 frame. And that's what stoichiometry is all about. Because we're going to learn that when we have a chemical reaction denoted by the following, we got A, oh, my pen has been acting up. A plus B to give me C plus D. Sometimes we put a coefficient up front, okay, like this. And this says that I need 3 A's to give me 2 C's. That's a stoichiometry. Or I need 3 A's to react with 1 B. Right here, that relationship. That's the stoichiometry of a reaction. We're going to learn all about that, but we got to balance chemical reactions, and hence that simulation I showed you in the additional resources. That's where it comes into assistance to help you out on how to balance chemical reactions. Okay, intermolecular forces, very important thing in chemistry. Earlier, I mentioned how we know that if I had a cup of water and a cup of honey, and I did the race to see who would empty that cup quicker, we all know that the water would empty out quicker because the water is not as viscous, okay? And it's not as viscous because the intermolecular forces right here, intermolecular forces, those are the interactions the molecules have with each other. If they're very strong, it has an effect on that type of property like the viscosity. So the intermolecular forces of honey molecules compared to the intermolecular forces of water molecules is much stronger, and hence doesn't flow as readily as water does, okay? And those forces, guess what, is related to the electrons around the molecules and how they interact with each other. So anyway, much more on that down the road, trust me. Now we're going to talk about solutions, and at the end we'll have a short conversation on gas. All right. Now, with respect to areas of chemistry, like any technical field, even medical doctors, as you well know, you have your heart doctor, your skin doctor, your bone doctor, your surgeons, your brain surgeons, anesthesiologists, etc. Well, chemistry is no different. In my particular area, that I got my background is organic chemistry. And as I mentioned before, those are mostly compounds that contain nothing but carbon, hydrogen, maybe some nitrogen and some sulfur. You have such things as inorganic chemistry that, yes, they do contain carbon and hydrogen, but mostly they contain a lot of metals, okay, in their chemistry. And in biochemistry, that's, obviously chemistry that deals with life, the bio. You're going to learn that chemistry is involved. Even, as we're sitting here, we got tons of chemical reactions occurring in our body. That would be an area of biochemistry, but chemistry no less, okay? We got physical chemistry. These are scientists that study physical properties of chemicals, how they behave. There are some chemists who get their doctorate, like Dr. Kim, the one who did the videos I mentioned earlier. She's got a doctorate in chemical education. She wanted to teach chemistry. So that's her emphasis. And then we got environmental chemists, and analytical chemists. Analytical chemists are very, very strict. They measure everything to the 0.0001 level. Okay, they're very specific, okay? Organic chemists, we're like to think of us as the crooks of chemistry. You know, yes, I know we measure things out, you know, maybe to the 10th of a gram, but unlike the analytical chemists, we're very rigid. They want to know, you know, parts per thousand per million. We're like, okay, put a 10th of a gram and put it together. We're not that sticklers for the numbers. Okay, our interest is if we made that compound. One reason I picked organic chemistry, because in synthesizing compounds, I showed you earlier that I used to be in construction, and in construction, I built things, we made things. We made them and we also destroyed them. And in building things, I found that organic chemistry was very analogous to that. You look at the structure of it and you figure out ways to make this compound. It's like building them, but only in the atomic scale. It's like construction, but in the atomic scale. Okay, now I would never say to you that chemistry is the most important class in your life. No, I wouldn't do that. But I will say this, that chemistry is literally is involved in 100% of your life, in all aspects of everything that is around us. You know, like I said, you just sit here listening to me. There's a lot of a lot of chemistry involved in your body. But making things, you know, like batteries and you know, bombs and energy and plastics and cell phones and etc. All of that involves chemistry. Even cooking. You know, I'm going to use food as a lot of examples, but there's a whole field, there's a whole scientific journal of food chemistry. Okay, food chemistry, and there are scientists that deal with cooking and in the chemistry of cooking and why, you know, certain things, you know, certain flavors and so forth. There are chemists who deal with perfumes and, you know, all kinds of, we're involved with a lot of stuff. All right, so we do utilize, scientists in general, you know, we utilize what's called the scientific method, which when you look at it, you kind of feel like, well, that's common sense. Well, that's the point. It is. A lot of the stuff is common sense. We're just making it aware that, okay, there it is. You may have been using this all your life and not knowing it. Now, you know, we got a name for it, the scientific method. Okay. And this starts off with making an observation of something. And so, for example, maybe you took a soda pop and you stuck it in the freezer, and guess what? It exploded. Okay. And you're like, oh, all right, what happened here? Okay. So you look at the mess. And after you clean up the mess, you're going to figure out what's going on. So you formulate a hypothesis. And that's essentially your best guess. What on earth happened? Why did it happen? And you may come to the conclusion in your hypothesis that water, when becoming ice, expanded. And when it expanded, it exploded the container. Okay. And so that's your best guess as to what could be happening. So you go research the literature, find out if anyone else has done anything along those lines. Okay, so you look at the scientific resources, gather as much information as you can, and then maybe you want to study this phenomenon a little bit more. So you may come up with performing some experiments of your own. You may want to try a different liquid. Okay, maybe try a different container. Maybe try a certain volume in a bigger container, see if that happens. You know, so you set up a series of experiments and see if you can repeat what happened to you in your observation. And just, you know, come up with some new hypothesis, or maybe the original hypothesis that you have still fits. And you may, after performing experiments, sometimes it happens, you may need to perform more, okay? Different ones. More questions come up and you need to answer them. So you analyze your hypothesis and repeat experiments as needed. After you're all done, you come to a conclusion, okay? And you may even, if you're lucky enough, write it up as a paper and send it out to some journal and publish your results, okay? And hopefully when you publish it, then other scientists around the world will repeat your experiment and hopefully get the same results as you did, okay? And if as time proceeds and more and more scientists and more other people around the world repeat what you repeat, that hypothesis may eventually be promoted to a law like the law of gravity. Okay, observations, very crucial, okay, very important. Things like color, clarity, states of the matter. We're going to be talking about only there's 4 states of matter: solid, liquid, gas. The other one is plasma. If you've ever seen the Northern Lights or maybe seen pictures of the Northern Lights, that is an example of plasma, the 4th state of matter. But we're not going to work with those. We're just going to deal with solid, liquid, and gas. Okay. And as I stated earlier, or maybe I didn't, matter is anything that has mass. Now, a word about mass. We tend to interchange the word mass and weight, okay, because we're here stuck on Earth. Okay, weight is dependent on the gravitational forces of where you're at. Mass is not. Mass is mass, regardless of where you're at on the universe. So your weight is much less than you're on the moon that is on the Earth, because of the lesser gravitational forces of the moon. But your mass is still the same. Okay. Having said that, the fact that we're here on Earth, we tend to interchange the word weight and mass. Okay, so keep that in mind. We're going to keep them the same. Rather, when we say mass, we're talking about weight. But keep in the back of your mind that it's slightly different depending on gravitational forces. We have concluded or have had the idea that all matter it consists of atoms, and we know that. So we're talking about the subatomic particles of the proton, neutron, and electron. We now know that those guys are even made up of smaller particles, which we're not going to talk about. That's beyond the scope of Chem 130. So we're going to keep it with the proton, the neutron, and the electron. Now, with respect to the states of matter, you're going to see a lot of diagrams that depict the different states of matter. Okay, so the one on the far left would depict a solid. Notice that the solids represented some compound or molecule represented by the round circles here, are all structured very ordered, and they're all close to each other. Okay, really close to each other. Now, if we look at the liquid, we still have the same structure. However, now they're not as rigid. They're moving, the molecules are moving around relative to each other. Okay, they can move around. Now, when we talk about intramolecular forces, as I mentioned earlier, we are talking about what is happening between here, those interactions between each other. Those are the intramolecular forces. Now, when we depict a gas, you can notice here now that the molecules are totally separated from each other. Okay, there's very little intramolecular forces interaction occurring for gases. Okay, because they're so far apart from each other. Also, they're very compressible. Think about it, because we can compress them closer together. There's a lot of space in between them. We can't do that so much with both the liquid and the solid because they're already close to each other. Now, the thing to keep in mind, if you look around the outside of these models of the sphere, around here, we have electrons on the outside, and I show that with the letters lowercase c superscript negative, because electrons have a negative charge. And so think about it. I got a molecule here with a lot of negative around it. Then I got a molecule right next to it with a lot of negative around it. Well, we know that negative and negative charges with the same repel each other. Okay, they're not going to get close to each other because they want to repel each other as much as possible. Okay, so they never ever touch each other. So something to think about when you grab something, pick something up with your hand. You got electrons down in the atomic scale on the outside of the atoms of your molecules of your finger, grabbing something that has also electrons. So you're never really truly holding something. Okay. Anyway, these are diagrams that we use to depict the different states of matter. Okay. Now, some properties about solids. Solids have a fixed shape and they have a fixed volume. Okay. Fixed shape and fixed volume. Now, even in the solid phase, obviously, and we go back, we can see here in the solid diagram that the molecules really are not moving away from each other. They're frozen, if you will. They're stuck in that position. But even being in that position, they are still vibrating. All matter still moves. Okay. There's only one time that matter supposedly will stop completely, and that's at absolute zero, which we haven't really reached that temperature yet. We'll talk about absolute zero down the road. Okay, so solid atoms will continue to vibrate, even in the solid phase. They have a crystalline structure, rigid. Sometimes, occasionally, they will not. Okay, they're not very compressible. Why? Again, the particles are already close together, and they're being repelled from each other because of the electron density around them. Okay. And we're going to introduce a property here called density. Density is a ratio, okay, given here on the right side. It's a ratio of mass over volume. We're going to be using a lot of ratios, and it's no different than the ratio of, say, speed, miles per hour, okay? Or the ratio of, if you're working, or what your pay rate, dollars per hour, okay? And with every ratio that we're going to be utilizing in this class, we can invert it, okay? So, for example, density is the ratio of mass over volume. Normally, the common units for mass are the units of grams, okay? And the common units for volume that we use more extensively than other units is the metric unit milliliter. So that is the units of density, okay? Grams over volume. And being the ratio, I can write it with grams over milliliters, or I can invert it with milliliters on top, grams in the bottom, okay? Keep this in mind, because in the next chapter, we're going to be dealing with conversion factors. And these are ratios that we can invert as we need. And which way we invert them is dependent on the units that we have to begin with. Because eventually we're going to set up these ratios side by side so we can chop off the units and get to the answer that we're looking for. Okay. So solids tend to have a higher density, all right, higher density than that material in their liquid state. Okay, meaning that matter is a solid will sink in the same material in the liquid state. The only exception is water. Water has a unique property in that when it freezes, just hit my elbow here in the funny bone. When it freezes, it actually floats. And you might ask yourself, "Oh, wait a minute." So here's a quick explanation as to why water floats. Okay. If I take 1 gram of water, let's take water, H2O, and I take 1 gram of water and I measure its volume. I take that 1 gram, weigh it, and then put it into an instrument that would measure the volume. Guess what? At 25 degrees, it also has a volume of 1 milliliter. So guess what? The density of water at 25 degrees Celsius is 1 gram per milliliter. Okay? That's the density of water. All right, so we use that as the reference point. Our benchmark is density of water. So anything with a density of greater than 1 would will sink in water. And anything with a density less than 1 will float. So why does ice float? Well, here, I'm glad you asked. If you take that same gram of water and you freeze it, that same gram, and you freeze it maybe in a little cube or something so you can do a measurement, measure the new volume, length, width, and height, right? Okay. Now you have a new volume. In fact, the volume is not 1, it's about 1.1. It's a little bit greater than the initial 1 in the liquid. This is in the liquid stage, and this is in the solid stage. Okay, as ice. So now you take that ratio, 1 divided by 1.1, guess what? Your new density now is about 0.9 grams per milliliter. 0.9. My pen's been acting up here. I don't know what's going on. I'm going to have to troubleshoot it this weekend. 0.9 grams per milliliter as ice, which is much less than 1, which means it floats. Okay. So now you know why ice floats. Because then ice, when it freezes, increases in volume. Very unique to water. Solids in the solid form are not going to mix with each other because they're locked in position. They won't diffuse very well and react with others. Liquids, the properties of liquids is, first of all, number 1 is they take the shape of the container, but have a constant volume. Okay, think about this. I got a gallon of milk in its gallon container. There's the shape of the container. I take that same gallon and I pour it into all that milk into a 55-gallon drum. Well, now the shape of the milk is different, right? It now has the shape of the bottom of the 55-gallon drum, but I still have the same volume. It's still 1 gallon. Okay? So changes the shape, but not the volume. Different liquids flow at different rates simply because of these intramolecular forces I mentioned earlier. Okay? Some are more viscous than others, and it has to do with how the electrons, how the molecules of whatever liquid it is interact with each other. Sometimes they interact strongly, sometimes not. And liquids, like solids, are not very compressible. They may be slightly compressible, but very, very low. Okay, because the atoms already, molecules are already close to each other, which is a good thing because with that, if that property wasn't true, we wouldn't have hydraulics. We didn't have hydraulics, guess what? You wouldn't have power steering, power brakes. Yeah, they would try to drive a car with no power steering. It's pretty rough. And no power brakes. Pretty rough too. Okay, so liquids, as far as their densities, they tend to have a little bit higher densities than gases, and liquids will not mix uniformly together if they don't have the same property. So normally, for example, if I make a mixed drink, let's say I take soda and water and some alcohol and I mix the two, I make a drink, right? They mix with each other. Both liquids, totally different liquids, but they mix with each other. It's because they had the same type of intermolecular forces that allow them to mix together. But if I take a liquid that say is oil-based and a liquid that's water-based, they do not mix. Italian dressing, classic example. I got 2 layers. I got an oil layer and an aqueous layer. They will not mix. Okay, with respect to gases, gases have no shape. They take the shape of the container like the liquids, okay? And they can expand and compress. Now, the volume increases as the atoms get further apart. Okay, think about this. It does make sense if you think about it, right? In that sense that the atoms get further apart, the volume gets bigger, right? And as the volume decreases, the volumes gets closer together. A good way to test this to see for yourself is get yourself a little balloon, okay? Get your little balloon, blow it up. You don't have to blow up very hard. You know, don't max it out, about maybe 3/4 of the way full. Tie it up, okay? Now, if you have a ruler, kind of measure the best you can the diameter, the distance of that balloon. Now take your hair dryer and don't hit it directly, put it on the warm side and warm up that balloon. Just warm it up, turn that balloon around and warm it up with the hair dryer. After a few minutes, measure it again. You're going to see that the balloon has expanded. Why? Because the heat of the hair dryer has caused those air molecules inside to get excited and they pull away from each other further away because they're picking up energy and the balloon expands. Now take that same balloon and stick it in the freezer for a few minutes. Take it out and now measure it. You will see that the balloon's diameter will decrease. Again, it's a function of energy because those air molecules that are high energy, now when you put it in the freezer, that high energy gets transferred to the freezer and it loses energy and the molecules start to come closer together. Okay? All right. Now, I can tell you right now, with respect to a specific volume, now I'll come back in a second. Gases have low densities. You notice gases like 0.001 grams per milliliter, much less than one, very low densities. And they will mix completely with other gases, regardless of the properties. And just that's the tendency because there's so much space in between them. Okay? And like air, for example, nitrogen, 78%, oxygen, 21%, etc. Okay. And gases exert pressure. Okay. Well, don't believe me? You know, check the pressure. Check the pressure. Let's say you got a tire and it is 30 psi, pounds per square inch. Well, you go to Circle K, Quick Trip, and get the air pump, and you pump in some more matter into your tire. What happens to the pressure? It goes up. You put in more matter into your tire, more molecules are bouncing up against the wall, the pressure goes up. Okay. All right, so with respect to shape and volume, solids have a fixed shape and they have a fixed volume. Okay. With respect to liquids, they do not have a fixed shape. They follow the shape of whatever container they're in, but they have a fixed volume. And gases, as liquids, their shape depends on the container, and they do not have a fixed volume. Right now, as it stands for Chem 130, at this point, we can answer no. Down the road, we're going to learn that only under certain conditions, gases will have a specific volume. Okay, but right now, the answer is no for a fixed volume. Okay, physical properties. Second. Physical properties and chemical properties. I kind of talked about that earlier. Physical properties are things or properties that do not cause. Well, I'm jumping ahead of myself. Let's talk about physical properties to begin with, and then I'll move on here in a second. They describe the appearance, okay, of the chemical, whereas chemical properties describe some facts about the chemical. Things like, okay, color, taste, odor, texture, at what temperature they mount, okay, whether it's a solid, liquid, or gas, even the density of that compound or the chemical, whether it's soluble in water, whether it's soluble in oil-like material, whether it can conduct electricity, and the hardness. These are all physical properties of a chemical. Whereas chemical properties talks about certain aspects of the chemicals. And for example, is it explosive? We all know that TNT, dynamite, is very unstable and very explosive. Okay, so that is a chemical property of TNT. Certain chemicals are corrosive. Certain acids, they touch metal, they tend to dissolve metal. They're very corrosive. Certain chemicals, by ingesting them, are poisonous. They're very toxic. Or they don't react at all. That's what the word inert means. Classic example of that is pure 100% gold. 100% gold is called the noble metal. It's called the noble metal because it doesn't react with anything. It's very inert. Okay. Whether materials reactive, whether it rusts or oxidizes, decomposes, things like that, these are chemical properties compared to the physical properties. Right. Now, with respect to the changes, the physical changes, we have things here that you're familiar with. I'm not going to tell you anything that you don't already know, but think about this. When you have a solid going to a liquid, don't we call that melting? When you have a stick of butter that you just took out of the refrigerator and put it in a hot pan, that stick of butter is nice and solid, right? Coming out of the freezer, stick it in the pan, what does it do? It softens up and it melts, okay? Think about this. This is all related to energy. When it's in the freezer, the molecules have strong intramolecular forces, okay? They're being held on to each other. Then you put the heat to it, you break up the intramolecular forces and they start to separate and it starts to move. Okay. All right. Going from a liquid to a gas, well, it's the same thing as when you take a pot of water, you want to make some spaghetti, you got to heat it up, right? It's called boiling. It's also called vaporizing, and it's called evaporating. Okay. A lot of liquids will just sit in there, will evaporate into the atmosphere on their own because the molecules in the liquid phase are moving around relative to each other. They're like, I don't know, the best analogy I can think of, have you ever seen how they select the Powerball, take the balls, they got the little ping pong balls with numbers and it's bouncing around, or bingo, they're bouncing around inside this container. And then that's the way what's happening in liquids are bouncing along each other. While the ones on the surface, they can be kicked out. They can be hit by another molecule, and with enough force that it kicks them out of the liquid phase and into the gas phase. Okay. And eventually, all that liquid will go into the gas phase because the molecules are moving around with each other, relative to each other, and working their way into the vapor phase, gas phase. Gas to liquid, we call that condensation. Okay, I got a glass of soda pop with ice here. On the outside, it gets a little cold, it gets a little moist. So I ask this question all the time, and I ask it, okay, where is that moisture coming from on the outside of my container? Anybody know where that moisture is coming from? Give me time to take a drink. My mouth is drying up. Okay, I got a nice cold container here. Got some ice in here. It's sitting here for a little bit. On the outside, I got a little moisture right here. Where's that moisture coming from? Magic, right? That's some Harry Potter stuff going on. Where is this moisture that we call condensation? Where would it come from? Anybody want to take a shot at that? What we got here? From the air, exactly, right? Because around us, we have water molecules in the vapor phase, high energy. Water molecules, vapor molecules have a lot of high energy. They bounce around trying to stay away from each other. Now, they come along and they hit the side of my container, okay, long enough so that the coldness, the energy they have is lost to the container, causing them to slow down. And when they slow down, other molecules, same things happen. Other molecules of water slow down. Eventually, they attract each other. Those forces come together, and they go back into the liquid phase. So eventually, on the outside, we get moisture coming down. No more moisture on the outside in the air. the more moisture in my container. Now, this might be a little bit different. You may not have heard of this, but this is going from a liquid to a solid. Oh, sorry, I meant the next one. Of course, you've heard of freezing, right? I could jump ahead of myself again. Yeah, when you get a liquid going to a solid, it's called freezing. Obviously, again, all this is energy related. Molecules are moving around. Whenever I take energy away from one system, I slow these molecules down. They will then transfer from the gas phase into the liquid phase. And if I continue to remove the energy away from it, it solidifies. It becomes solid. It's without freezing. This is the one that you may not be familiar with. This is when a solid goes directly to a gas. Okay. And there's two classic examples here. Maybe you might be familiar with some of these. Sometimes for closets, people put these tabs called naphthalene tabs. Kind of, I don't know, they have a chemical odor to them. Sometimes you even find them in urinals. That chemical, smells somewhat fresh. I'm not particularly keen on it. But that chemical, that solid, is bypassing the liquid. At least it's going through the liquid, but very short time period, and then moving right into the gas. Another classic example is carbon dioxide, okay, or dry ice. Dry ice is nothing more than carbon dioxide. Carbon dioxide, which is a gas, is put into this carbon dioxide machine that basically you bring the carbon dioxide molecules closer together, the forces start interacting with each other, and then they go into the gas phase. So you got this chunk of dry ice, which is not really water, it's carbon dioxide. Okay. And that smoky stuff that you see coming out, that's CO2 coming off carbon dioxide. And because it's so cold, the moisture around us is freezing. So you're seeing water vapor around condensing the clouds. Okay, because the carbon dioxide itself is colorless. Now, so you can go to Fry's, for example, and get some carbon dioxide. Now, let me ask you this as a little bit of a side note. I tend to use a lot of side notes too. Why, if you have a lot of plants at home, why would you want to go to Fry's to pick up some carbon dioxide to put on or near your plants? So put on your plants because it's cold, might kill your plants. But why would you put it around your plants? Okay. Or alternatively, you could talk to your plants. Why would you want to do that? Any idea why you want to get some dry ice and put near your plants? I know you're probably thinking, I don't have any plants, but let's assume you do. Anybody want to take a shot at that? You can type it in or unmute yourself, either way. Remember what I said about dry ice is carbon dioxide. What we got? All right, somebody took a shot. Let's see what it is. It's like food. Yes. Okay. Kind of. It's like oxygen to us. We need oxygen. Okay. Plants need carbon dioxide in their metabolism. Okay. And so by putting carbon dioxide, they will take it in and utilize it, and then they give you in return oxygen. So here's the cycle. Okay. Now, why would you talk to them? Other than psychological reasons, why would you talk to them when you can't get any dry ice? Can I get the thinking caps rolling? Your breath, okay, but what's in your breath? You're correct, that's carbon dioxide, very good. one of the gases we have, our byproducts is carbon dioxide. And so by talking to them, they benefit by picking up carbon dioxide, and then they return the favor by giving you oxygen. Okay. All right. So sublimation is the process of going from solid to gas. I like the way you guys are thinking. Okay, because I'm big on let's get the brain working and applying bringing in other information overall. You'll see some examples, quite a bit of examples of that. Okay. All right, deposition, and that's how we make dry ice. We take a gas, run it through that dry ice maker, and it's called deposition. Okay. Now, when we look at physical changes and even chemical changes, we depict them by this process using this arrow here. See this arrow shown right here? Okay. What we show is that on the left side of this arrow are the oh my goodness, my pen just doesn't want to reactants. Okay, here's the arrow. And then on the right side of this process, which could be a physical process or a chemical process, we have the product. Okay. And so we look at this arrow. On the left side is the reactants, and we look at H2O. Okay. Now of course, we don't know what it's a subscript. We know just by the subscript that there are 2 atoms of hydrogen per 1 atom of oxygen. Okay. We're going to learn how all that's put together. Okay. We can see on the left side of the reactant side that we have H2O. And if we go over to the right side and the product side, guess what? It's still H2O. Nothing changed structurally. Okay, so that implies that we have a physical change. We can further identify the state because what we have here, the atom in parentheses, is the liquid phase, and the G, lowercase g, is the gas phase. So this is an example of a process of water going from liquid to gas, and we call that boiling. Okay. And this whole thing we just talked about is very nicely put together for you here in this diagram. And it's all about energy. Okay. The thing about Mother Nature is this: energy always goes from a high state to a low state. Okay. Remember that. To put it up from a high state, we need to put energy into the system. For example, to go from a solid to a liquid, we need to put energy, which I want to denote as E plus. We got to put energy into the system. And what we're doing in doing that, that energy is utilized to break up the interaction between the molecules, breaking them up, not making it as rigid, causing these molecules to become more fluid. Okay. And if we continue to pump energy into the system, we eventually cause these molecules to separate completely apart and enter into the gas phase. The other direction to the left is energy is lost, the loss of energy. And so we have a gas like the air molecules around us, okay, and they hit my container, and that energy is lost, and then it causes, by that loss of energy, causes those air molecules, water molecules to condense and go into the liquid. Okay? So it's all function of energy. Okay. So atoms are always moving, even in the solid state. Okay. More on physical changes. When you obviously heat ice, the water molecules are gaining energy. Specifically, it's called kinetic energy, movement energy. You know, think about this. You're at the beach, okay? The beach is the sand itself. You got a beach, sandy beach. The sand is about 100 degrees. Okay. You gotta walk barefooted from point A to point B. Now, are you gonna nonchalant walk across that beach with no shoes on and just, suffer? Or are you gonna run? Okay, now, I bet unless you got some real tough skin under your feet, you're gonna run because that beach is pretty warm and it's forcing you to pick up some kinetic energy to get out of there and move faster. Okay. All right, so when particles gain enough energy, they overcome these forces I just talked about, and then therefore the solid will melt, go from a solid into a liquid. Okay. And if you continue to heat that up and give it more energy, it will eventually go into the gas phase. It's all by energy. It really is. All right, chemical changes. Here, the chemical composition is totally broken down and you create something new. Molecules break apart and they rearrange and form new compounds. Okay, we call these chemical reactions. Keep in mind, of all through chemistry, there's only 6 types of chemical reactions. We're gonna talk about them. We're gonna introduce 1 or 2 here in a bit. Okay. So a starting substance is totally the chemical structure, totally broken apart. And a new substance, new materials made. For example, if you were driving your vehicle today, you went from point A to point B, you used gasoline, fuel, you burnt some compound, okay, totally destroyed it, and you created carbon dioxide and water. What I have here is a chemical formula, okay, again denoted by the arrow. Okay, I have a general formula here. This general formula represents hydrocarbons. Why hydrocarbons? Because they're made up of nothing but hydrogen and carbon. And X represents a number. So this is a general formula. The smallest one is C1H4. Which is methane. Smallest hydrocarbon, and there's a whole bunch of other ones, a whole slew of them. My pen just. All right. So for Chem 130, okay, this is called a combustion reaction. And the combustion reaction consists of a hydrocarbon in the presence of oxygen, which you cannot burn anything without oxygen. So oxygen is a reactant. And for Chem 130, you're only going to make 2 products, carbon dioxide and water. Okay? Carbon dioxide and water. If you're ever in front of behind a vehicle, look at the tailpipe, and sometimes you see some that are dripping liquids out of the tailpipe, and what you're seeing is a little bit of water coming out. Okay? That's from the combustion that they have. Now you might say, well, wait a minute. Okay, I also have carbon monoxide, and that's true. That's why I said for Chem 130, because we're assuming we got 100% efficiency with respect to this combustible machine that is burning it, and it's not. Our combustible machines are probably somewhere in the order of 30% efficient. And yes, there is carbon monoxide coming out of the exhaust and poisonous gas because of the lack of the efficiency. All right. So burning gasoline, the structure of your reactant reactants is totally displaced. Okay. Notice, but here's the other takeaway from this. The carbon in the hydrocarbon is still carbon as in the form of carbon dioxide. Nothing has changed. It's still carbon, okay? It's just in a different form. Just like the food that you ingest, you take that material, nutrients from, if you eat a hamburger, You incorporate that into your body. If it's carbon in that hamburger, you incorporate it into your body so to make, muscle fiber, in my case, a little more fat fiber, okay, cells. That carbon is still carbon, it's just in a different form. All right, indicators of a chemical reaction. Here we got about 10 more minutes and then we're gonna call it a day. I'm pretty good. My other class is about and up 5 slides behind you. All right, indicators of a chemical reaction. What is it you see? You're observing. What tells you that possibly a chemical reaction proceeding? Well, for example, if it burns, that's a good hint that something is a chemical reaction, right? You're burning some wood, you know that the ashes left over are not going to revert themselves back to the wood. Okay, so burning, rusting, that's a good indication that you have a chemical process. Okay, you might have release of gas bubbles without heat involved. A good example would be an Alka-Seltzer tablet. Alka-Seltzer tablet, you take it, you dump it in water, and it starts to fizz. Okay. But here's the thing about that Alka-Seltzer, the little side note. In that tablet, if you look at the labels, all you have in there is sodium bicarb and maybe some citric acid. And once they hit the water, the binder that holds the tablets together dissolves, and all the ingredients get moved into solution. Now the citric acid now reacts with the sodium bicarb, and it releases carbon dioxide, which is the bubble. As far as I know, there's no medicinal value involved there. So anyway, the same thing happens. Similarly, if you're making chocolate chip cookies, most recipes call for baking soda, sodium bicarb. Any idea why? Any idea why you put baking soda in your chocolate chip cookies? Or for that matter, if you're making bread, why would you put plant bugs in your bread? Any idea? Well, in both cases, the sodium bicarb, when you're making your cookies, decomposes in the heat, releases carbon dioxide, which causes your cookies to rise. Otherwise, you're going to have flat cookies. Same is true for the bread. The yeast, I call them the bugs, start breaking down the material. One of the byproducts of plant, which is yeast, okay, is carbon dioxide, which causes your bread to rise. Okay. All right. Formation of a solid is a good indicator. You might get two liquids that you mix together and poof, you get a precipitation, solid forms. And that's a good indicator you have a reaction that preceded, or it might give off heat. If you go to, say, CVS pharmacy, you buy both a hot pack and a cold pack. You get that hot pack, you get it, you smash it together, it gets warm. Okay. Good, another indication of reaction. Or the cold pack, same thing, smack it, gets cold. Okay, another indication of a chemical reaction. Or, you got these glow sticks where you take them, crack them in the inside is you're releasing those two chemicals so they can mix. And in the process of that chemical reaction, light is given off. So light is given off, good indication. The old flash cubes, if you use the old flash cubes to take photographs, you use magnesium wire, they burn and you release a lot of light. Or it could be a change in color in your material or an odor. Okay. Classic example would be wintergreen. Okay, wintergreen is made by two different compounds. One is an alcohol and one is an organic acid. Separately, those things don't smell very good, but you mix them together, you form what's called an ester, and you get wintergreen is one. Another one is the banana oil is an ester. Smells pretty good. At the same token, you can make chemicals that have sulfur-based compounds and they don't smell very good at all. Okay, let me go through this reaction here, and then we'll call it a day. All right. So this is a reaction between the element sodium. You know, I said the element. It's not sodium like table salt sodium, sodium chloride. This is the element sodium and chlorine gas. Okay. When they react, they will produce the solvents, which better known as sodium chloride, which totally different properties. Okay, so here we go. On the left, far left, one of the reactants is sodium. Okay, then notice the coefficient 2. We have this balance. We have 2 sodiums on the left of the arrow, and guess what? 2 on the right of the arrow. We got 2 chlorines on the left of the arrow, 2 chlorines on the right of the arrow. This is a balanced chemical reaction. It's assumed that it's a 1 here, like in mathematics. You don't need to put a 1. And guess what? The stoichiometric relationship. Remember when I talked about the stoichiometric relationship? Is a 2-to-1 ratio, 2 sodium for every 1 chlorine. Okay. All right. So here's your first chemical reaction. Now here's a picture of sodium metal. Sodium metal is a very reactive metal. You can get on YouTube and search for sodium metal reacting in rivers and streams. People have taken big chunks of sodium and dumped them in there. It's quite drastic reaction. Sodium reacts violently with water, produces a lot of heat, produces hydrogen gas, which causes a boom. Okay. It's so reactive that when we make it and we have to store it under mineral oil because we can't store it out in open air, it will react. Very reactive metal. Chlorine is a poisonous material. A lot of people, a lot of companies and municipalities use it to treat their water treatment, get rid of bacteria. Very effective in that. Also, swimming pools sometimes they use chlorine to clean up their water. And if you live around one of these, and if you ever see a yellow cloud, please quickly get upstream, upwind, I should say, because this chlorine is a poisonous gas. All right. When you mix these together, denoted by the plus symbol here, saying I'm mixing my 2 reactants together, you get something here that you can put on your French fries. Okay. This is sodium chloride. Notice I call this chloride. Okay. As compared to chlorine. The element is called chlorine. The electrolyte, the ion is called chloride. And so, sodium chloride is not hazardous as poisonous gas or very reactive metal. It is hazardous if you got high blood pressure and you want to stay away from sodium, right? Okay. And here's the fascinating thing about this, for me at least, is that there are 2 electrons. I denote that by the letter lowercase c and superscript minus, because the electrons have a negative charge. There's a transfer of 2 electrons from the sodium to the chlorine. Okay. And these electrons, when we compare the size, the weight, the mass, as compared to the proton and the neutron, the electron has a relative mass of 0. And it's like maybe taking like 2 hairs from my head and totally changing my personality. Yanking them out, I become who knows what. And 2 electrons, those little electrons got transferred. The same electrons you have, similar, I should say, that in the morning when you wake up, you got long hair and your hair's like this. Oof, you got a bad hair day, got that static charge to it, or you're walking on carpet and you touch metal and you get zapped. Those are electrons roaming. And just the transfer of 2 electrons has a drastic change on the properties of your products. Quite impressive to me. Okay, well, I tell you what, I have 4 p.m. here, and what we'll do is we'll stop here, slide number 22. Okay, I will upload